How are you all? I hope you all are doing wonderful. So the JEE Mains first attempt is already over. So students who haven't performed well in their first attempt, don't worry, you still have your second attempt to go. The only thing that you need to be very careful about is start revising the topics and start making short notes, and also simultaneously prepare the previous year question solving sessions. So if you were already familiar with this particular question solving sessions, I was covering the PYQ of JEE Mains of different topics of mathematics, but due to my own involvement in college and my examination, I couldn't continue. Okay, so I'm extremely sorry for that. So I got time now, and I will be trying to be continuous from now onwards. Okay, so let's get started on the today's JEE Mains previous year question solving sessions, and the today's topic will be matrix and determinant. So matrix and determinant is an extremely important topic, and if you look at the JEE Mains previous year paper and of the first standard, of course, so you can see that matrix and determinant questions were there, okay, in number. So with this, you can understand how important this particular topic is, because matrix and determinant has its importance in vectors and 3D geometry as well. So with these things, let's get started. So today's goal is basically to solve the top important question on the topic of matrix and determinant. Let's get started. So the very first question is on our screen. So students who are familiar, I would recommend to all of you to pause the question at this particular moment and try out this particular question on your own. Okay, so this question is from the property of matrices. Let us study what the question says. So we have given a square matrix of order 3 cross 3. So order is, so if you look at the order of the matrix is 3 cross 3. So order is 3 for a square matrix. And it is said the determinant of this particular matrix A is given as 2. So we know how to calculate the determinant of this matrix. So let us use this particular data. The determinant of matrix is basically 2. So from here, if I calculate the determinant, I will be getting the value of this unknown alpha. So let us do so. So if I calculate with using the first row, okay, so this is a 1 multiplied with the cofactor of this particular corresponding this element. Okay, so cofactor will be basically 3 into 2, that is 6 minus 1, so that is 6 minus 1, and then this particular element will have a cofactor of minus 1, so minus 2 multiplied with the minor, so that will be 2 alpha minus 1. Okay, and then plus 3 times of, then we will have this is as alpha minus of 3, and this matrix determinant value is given to as 2. So from here, if we solve this particular problem, I will get the value as 5 minus 4 alpha and then plus 2 plus 3 alpha, and this is basically minus 9 is equal to 2. So from here, I will get the value as minus alpha, okay, and minus alpha, and if I sum up this, 5 plus 2 is basically 7, and then 7 minus 9 is minus 2. So alpha minus 2 is equal to 2. So from here, if I solve, if I take alpha on this particular side, so the value of alpha will be equal to minus of 4. So from here, I get the value of alpha as minus 4. Okay, so the very first unknown, that is alpha, is basically found in this particular problem in the fashion alpha is equal to minus 4, and I use the information that is determinant of A is equal to 2. Now what further information is provided to me is that, so if I look at the further information that is given as 2 times of adjoint of 2 times of adjoint of the 2 times of determinant of A, and if you take the modulus sorry, and if you take the determinant value, and the determinant value is provided in the question to be 32 to the power n, so we have to look for the value of 3n plus alpha. So alpha is already found out, so we have to find for the value of n. Now if you have studied the properties of adjoint, so let me write over here the properties. So yeah, we have the important property that is known as the king property, that is matrix A into adjoint of matrix A is basically equal to determinant of matrix A into identity matrix of the order n. So if the matrix A is of order n cross n, so we have this particular important property. So using these particular properties, we can definitely add to the of the important result, that is determinant of adjoint of A is basically equal to determinant of A to the power n minus 1. And similarly, if you have a constant multiplied with the, so multiplied with the determinant of A, and this particular result is basically equal to k to the power n into determinant of A. And similarly, there is another important result, that is k into adjoint of A is the whole of determinant will basically be equal to the k is basically a constant number, so is basically equal to k to the power n minus 1 into determinant of A. So if you know these particular properties, then you can definitely approach this particular problem. So let us solve this. So firstly, I will take this constant 2 out of this particular determinant, so this will be opened as 2 to the power n, and that is basically n over here is basically 3, so that is 3. So 2 to the power 3 into determinant of adjoint of 2 times of adjoint of 2 times of determinant of A. Okay, and that is result is given as 32 to the power n. So I can simplify 32 to the power n as 2 to the power 5n. Okay, so if we solve further, so from here I can solve this as, so this is 2 to the power 3, that I can write this as 2 to the power 3 into adjoint of now whatever property I will use is basically, so adjoint of 2 times of, now adjoint of 2 times of a can also be written as 2 to the power n minus 1, that is 2 to the power 2 into adjoint of a. Okay, so, and this particular value is given as 32 to the power n, that is 2 to the power 5n. Now, what property I used over here is basically, so if you look at the property, that is adjoint of k into a, and is determinant of this particular thing is basically equal to k. So if you take from here, that is basically k to the power n minus 1, okay, k to the power n minus 1 into adjoint of a, okay, k minus 1, and the whole of this determinant. Okay, and similarly this particular property, sorry, oh, okay, I wrote a wrong result over here. So this is similar to this particular result of determinant only. Okay, I'm very sorry for this, that is k to the power n only. I wrote k to the power n minus 1. So with this, if you solve this problem, so from here you can and you can arrive to the result is 2 to the power 3 that is 2 to the power 3 into, and if you take the 2 to the power 3 out of this particular adjoint, then this will be 2 to the power 3 whole to the power n minus 1, that is 2 to the power, there is 2, that then this will become 2 to the power 6 into adjoint of a. Okay, so and the denominant value is equal to 2 to the power 5n. So from here if you solve, and this is again a constant number, so this will be coming out as 2 to the power 3 into 2 to the power 6 whole to the power 3 into adjoint of a. Okay, and determinant of that, and is equal to 2 to the power 5n. Now if you solve further, so from here this result will be equal to 2 to the power, so you can solve this at 2 to the power 18 plus 3 is basically 2 to the power 21, and adjoint of a is basically given as a, determinant of a whole to the power n minus 1 whole square. Okay, so that is n minus 1 is basically 2, and 2 whole square is basically 4, so that will be equal to, so determinant of a will be a determinant of a to the power 4, and that is equal to 2 to the power 5n. Now we are provided the data that determinant of a is basically equal to 2. So from here if I solve this, this will be 2 to the power 5n is equal to 2 to the power 21 into 2 to the power 4. So from here the value of n is equal, so value of 5n is equal to 25, and if you solve this, the value of n is equal to 5. So from here I got the result of another constant unknown value, that is n is equal to 5. So if you solve this, and then you solve this particular result, that is 3n plus alpha, and the value of 3n plus alpha will be equal to, so n value is 5, so 3 into 5 15, 15 plus minus of 4, so that the value will be equal to 11. So with this, the right answer to this particular problem will be option number A, and that is 11. So I hope you have solved this particular problem. So quite an interesting problem based on the properties. So if you are familiar with the properties, you can definitely solve this particular problem. Okay, so let me write another property which I used over here. So the property which I used in this particular position, okay, so let me write for the property which I used in this particular position is this, that is adjoint of a, and if you continue this is n times or k times, whatever you write this as adjoint of, and you continue this as k times, okay, and then take the determinant of this particular value, this value will be equal to determinant of a to the power n minus 1, and if you continue it for k times, then to n minus 1 to the power k. Okay, so this is a result which you must remember. Okay, and with this, if you use all the properties, you can definitely arrive to the conclusion of the value of n, and you have the value of n and alpha, then you can compute this result of 3n plus alpha, and the answer to this particular problem is option number A. So yeah, this question is done, and let's move to the next problem. So the next problem is again on a problem which is on the based on the question of system of linear equations. Okay, so you have provided with three equations with three unknowns. Okay, so we have to find this particular solution of the equation, and it is already mentioned in the problem that this particular solution or the equation set has infinitely many solutions. So in this particular problem, if you are provided with a question where there are infinitely many solutions, so you must have remembered the Cramer's rule. Okay, so the very first thing you have to solve for is the determinant value of the coefficient matrix, and that is delta. And similarly, if you replace the coefficient matrix of the coefficient matrix with the first column of the coefficient matrix with the constant values, then you get the determinant, that is delta 1. And similarly, if you replace the second column with the constant matrix, then you get delta 2, and similarly third column with the constant matrix you get delta 3, and this all of these are equal to 0, then only you get the solution for infinitely many solution. Okay, infinitely many solution. Okay, so which is actually said in the problem. So for infinitely many solution, you must have all this determinant equal to 0. So let us solve for the determinant. Firstly, the determinant of the coefficient. So if I construct the determinant of the coefficient, this will be 2, this is 1 over here, and this is minus 1, and similarly this is 2, and this is minus 5, and this is lambda over here. Okay, and similarly this value is equal to 1, 2, and this is minus 5, and this result of the determinant would be equal to 0. So if I solve this particular, so let me solve this. Okay, so let me expand this on the first row only. This will be 2 into 2 into this will be equal to 25 minus 2 lambda minus 1 times of, that is be equal to minus 10 minus lambda, and then it is minus 1. Okay, so from here this will be, this is minus 1 of, and this is going to be 4 minus of minus 5, that is plus of 5, and the value is equal to 0. So from here if you solve this particular equation, then you basically get to the value of lambda. So this is a linear equation in lambda, and this value will be equal to 50 minus 4 lambda plus 10 and then we have plus lambda minus 9 is equal to 0. So from here you get to the value of lambda. So from here you get to the value of lambda as, so that is equal to 3 lambda is equal to 51. Okay, 3 lambda is equal to 51. So from here you get the value of lambda as 17. So from here you get the value of lambda as 17. Now once I have the lambda value of 17, the only challenge is to find the value of mu. So let us apply the other determinants values. Okay, so if I construct lambda 3, okay, so if I use the value of determinant of 3, that is the replacing the third column with the constant matrix. Okay, so that determinant will be constructed as follows, that is 5, and from here, so what I did is basically, this is basically equal to 2, sorry, the value over here is equal to, this is 2 2 and 1, so this will be 2 2 and 1, and similarly this forward will be 1 minus 5, 1 minus 5, and over here is 2, and over here is minus 1, sorry, this will be replaced by the constant values. Okay, that is be equal to, so this value will be equal to, so this value will be equal to 5 mu and 7. Now if you construct this determinant and equal it to 0, you will get the value of mu. So from here if you solve this, so let me solve this. Okay, this will be equal to minus 35 minus 2 mu, okay, minus 1 times of, and this is going to be 14 minus mu, and this is going to be plus 5 times of, and it is 4 minus of minus 5, that is plus of 5, and is equal to 0. So from here if I solve this, this is minus of 70, okay, minus of 4 mu, and this is minus of 14, plus of mu, plus of this is 9 into 5, that is 45, and is equal to 0. So from here if you solve this, the result will be going to be, so this is 70 plus 45, okay, minus 70 plus 45 is coming out as minus of 25. So minus of 25 and minus of 14 is going to be minus of 39, and minus of 39 minus of 3 mu, so from here is equal to 0. So the value of mu is equal to minus of 13. Okay, so the value of mu is equal to minus of 13. So if I have the value of mu and lambda, I can definitely evaluate this particular expression. Okay, so I can evaluate this expression, that is lambda plus mu whole square plus lambda minus mu whole square, and the value will be equal to, so I am letting compare, okay, doing it over here. So lambda value is basically 17 and mu value is 13 minus 13. So 17 minus 13 is 4. So 4 whole square plus, and lambda value 17, 17 minus or minus 13 is going to be plus of 30. Okay, so plus of 30, 30 whole square is 900. So let me write it 30 whole square, and the result will be coming out as 916. So with this, the right answer to the particular problem is going to be option number A. So the A is the correct answer to the particular problem. I hope you have solved this particular problem and you got the answer as option number A. With this, let us move to the next problem. And the very next problem is basically a problem which is which comes very repeating. Okay, because this is a very interesting matrix, and this is known as the upper triangular matrix. So you can, if you can observe, this is an upper triangular matrix, and upper triangular matrix actually follows some properties in multiplication. So over here, if the determinant matrix A is basically given as 1 1 by 51, and this 0 and 1 over here. So and then we have given with the matrix B, there is another matrix B which is constant in the fashion, that is 1 minus 1 2 minus 1 into matrix A, that is 1 1 by 51 0 and 1, and then multiply with minus 1 minus 2 1, and 1 over here, okay, minus 2. So if you solve this and if you compute the result of the product of this particular three matrices, okay, so you will find out that you will find an interesting result over here, okay. So let me do it. So computing this results, okay, so let us compute this result. uh, let us use a white color, okay. Now if I compute the first two matrix product, okay, so if I compute the product of the first two matrices, okay, because what is B, so I can write this B as, so let this particular matrix 1 2 minus 1 minus 1 as C matrix, and this A, and the last matrix is D, okay. So the importance of doing this as, okay, so if I have the matrix B as this particular value, then B to the power n will basically multiplication of these matrices n number of times, okay. So these matrices are multiplied as n times, okay. Now if I multiply this matrix n times, so what important result that you will find out as this as, so if you look at matrix D, okay, now instead of multiplying these matrices, okay, what interesting result you will find out is that if you compare, if you compute the result of, if you compute um, D into C, okay, let us compute D into C and let us get us what we find out. This is 1 2, this is minus 1, sorry, minus 1 minus 2, this is plus of 1 and 1, and multiplied with another matrix that is 1 2 minus 1 and minus 1. Now if I compute this result, I will get the result as, so minus 1 into 1 and minus 2 into minus 1 is basically plus 2, so minus 1 plus 2 is coming as 1, and similarly this result will be coming out as, so, and if you compute this result, this will be 0, and this is going to be 0 again over here, and this is 1, okay. So we get an identity matrix of order 2 cross 2, okay. So we get an identity matrix over here. So what important thing is that is product of D and C is basically equal to identity matrix. That means when I have B to the power n, so in this value, when I have to compute for B to the power n, that is CAD into CAD, and this is continued n number of times, okay. Now what important result is that C into D, sorry, D into C, that is a product of the matrix is D into C is basically identity matrix, and similarly this particular chain of results will go on until here, and so we will get the result is of this particular product as simplified as C into A to the power n into D, because multiplying with identity matrix doesn't change the matrix. And similarly, the result of B to the power n is going to be simplified as C into A to the power n into D. Now, what important result is basically correspond to this upper triangular matrix of A is basically, if you compute the square of this triangular matrix A, that is 1, 1 by 51, and this 0 and 1, and then multiplied with, so with this, if you compute the result is coming out to be as, so from here this is 0 1 0 and 1, and similarly this result will be coming out, this particular element is going to be come out as 2 by 51, okay. So this result is going to be coming out as 2 by 51. Now similarly, if you compute the result for a to the power 3, you will get the result as 1 0, and over here it will be 3 by 51, and this will be going to be 1 again. So similarly you get a pattern which follows, okay. So that means a to the power n is basically going to be of the fashion 1 0, and this is going to be n by 51, okay, n by 51 over here and 1 over here, okay. Now we have this particular result. Now if I compute for the result of, that is B into a to the power n, now from here if I compute the result of C into a to the power n into D, so the result is going to be coming out as 1, so this is 1 2 minus 1 minus 1, and this matrix is going to be 1 0 n by 51 1, and then this matrix is going to be minus 1 minus 2 1 and 1. Now if you compute the result, this result is going to be coming out as, okay, so you can definitely compute this result on your own, and you will find out the result is 1 n by 51 plus of 2 into minus 1 minus n by 51 minus 1 multiplied with the matrix, okay, multiplied with the matrix, that is minus 1 minus 2 1 and 1, and if you again simplify, if you simplify this again, and the result is going to be coming out as, okay, so n by 51 plus 1 n by 51, and this is going to be minus of n by 51, and this is going to be 1 minus n by 51, and this is given out as the problem as basically B of n. Now if I have the value of B of n, and what is basically we need to find is basically we have to sum up for all the elements, okay, we have to sum up the matrix addition of B into n from n equals to 1 to 50, and if you do the summation, if you put the summation, that is basically correspond to summation of all the individual elements for n belonging to 1 to 50. So for n belonging to 1 to 50, we have to compute the summation. And if you can compute the summation of, so we know this results, okay, that is summation of n is basically n into n plus 1 divided by 2. Okay, so if you do this particular summation values, you can find out the problem. You can find out in this particular problem the result is going to be coming out as, so this is 50 plus 15 to 51 by 2, that is 25 by 51, sorry. So let me write this over here. Okay, and you can compute the similar elements. Okay, and you can compute over here. Okay, I have done it on my own and I got to the result. The conclusion is basically, and I got to the conclusion that is from here, the summation of this particular B matrix, B to the power n matrix, is coming out as, so from here the result is coming out as 75, 25, minus of 25 and 25. So in this particular problem, we have to ask for the sum of all the elements of the matrix, of this matrix summation of b to the power n. So if I compute the summation of all this matrix, I am going to be getting the result as 100. So which is option number C is the right answer to this particular problem. So the next problem is given as, the matrix A is given as 1, 5, lambda and 10. So we have to find for the inverse of matrix A as alpha times of A plus beta times of I, and we are also given with the value of alpha plus beta is equal to minus of 2. Then we have to find for the expression. Then we have to find for the expression of 4 alpha square plus beta square plus lambda square. Now we know the inverse of 2 cross 2 matrix as 1 by determinant of A. Okay, so 1 by determinant of A, that is going to be 10 minus 5 times of lambda, and in the matrix you interchange the diagonal elements as 10 and 1 over here, and the non-diagonal elements with a negative sign, that is minus 5 and minus lambda, and this value is basically equal to alpha times of A plus beta times of identity matrix. Now you can compare the result and perform over here. So alpha times of A, that is alpha, okay, 5 alpha, lambda alpha and 10 alpha, okay, plus and beta times of identity matrix, that is beta 0 0 and beta, and is equal to the A inverse. So from here if you compare the elements, okay, so from here let us compare the first row first element. I will get the value as, so if I compare the first row first element, I'll get the value of alpha plus beta is equal to, 10 divided by 10 minus 5 lambda. So from here we are already given with the result, that is alpha plus beta is equal to minus of 2. So if I interchange the value, so from here if I replace alpha plus beta is equal to minus 2, so from there I will get 10 by 10 minus 5 lambda is equal to minus 2. And now if I solve this, that is 10 by 10 minus 5 lambda is equal to minus 2. So if I solve this result, I am going to get minus 5 is equal to 10 minus of 5 lambda, and from here I'll get the value of lambda as, so 5 lambda is equal to 15, and the value of lambda is basically 3. So from here I get to the value of lambda as equal to 3. Now if I have the value of lambda as equal to 3, I can substitute in the corresponding results and I can get, so let me compare the first row second column element, that is going to be 5 alpha. So that is going to be coming out as 5 alpha, and it is equal to, and that is equal to minus 5 divided by 10 minus 5 lambda. Okay, and that this value is going to be coming out as 1. So if you solve this, so this is going to be, so if you in place of lambda if you put 3, this minus 10 minus 15, that is minus of 5, minus 5 divided by minus 5 is going to be 1. So from here the value of alpha is going to be coming out as 1 by 5. And similarly if you solve for the for another element, that is you can take this element, the second row second column element 10 alpha plus beta is equal to, so you can take the element as 10 alpha plus beta is equal to 1 divided by 10 minus 5 lambda, and if you solve this particular results, you will get the value of beta as minus 11 by 5. So from here you get the value of beta as minus 11 by 5. So we have the values of all the unknowns, that is alpha, beta and lambda. Now if we have the values of the unknown alpha, beta and lambda, we can find out the expression, the value of the expression 4 alpha square. I can find out the value of the expression 4 alpha square. So okay, 4 alpha square, and that is going to be 1 by 25 plus beta square, that is going to be 125 by 25 plus lambda square, and that is going to be, and lambda value is 3, so that is going to be plus of 9. Now if you solve this particular result, okay, you can solve this result over here. So let us evaluate the result. Okay, so from here if I evaluate the result, that is going to be coming out as 126 by 25 plus of 9, and that is going to be coming out as 126 plus 1, there is going to be 225 divided by 25, and you can solve this result. Okay, I hope I'm doing, oh sorry, there is not 126, that is going to be 125. Okay, I'm very sorry, this is going to be 125, and 125 plus 225. Okay, 125 plus 225 divided by 25, and that is going to be equal to 14. So with this, the right answer to the particular problem is going to be option number D. Is going to be option number D, that is 14. So I hope you are able to solve this particular problem. Alright, so the next problem is on our screen. Pause the video and try to solve this question on your own. Let us get started. So it said that there is a matrix A, and the matrix is a 3 cross 3 matrix given as 1 0 0 0 0 over here, and 4 minus 1 is 12 and minus 3. Now interesting thing about this particular matrix is that if you compute the result of A square, what you will find out is that, let us compute, okay, that is 1 0 0 0 0 over here, 4 minus 1 12 and minus 3 over here, and multiplied with the same matrix. Okay, so if I compute the result multiplying with the same matrix, I'll get to the value as, so let me compute and find out the value. So if you compute and find out the value, the result is going to be 1. So over here there will be 0 and 0, over here also 0 and 0. And similarly for this middle element, you will find out when you multiply the second row with the second column, you'll find out the value as, okay, so you can find out this values also will be coming out as 4, and similarly this result will be also coming out as minus 1, and similarly this is also be coming out as 12, and this minus 3. So that means the value of A square is equal to A. So such matrix is basically an idempotent matrix. That means A is basically an idempotent matrix. Okay, idempotent matrix. Okay, so such a matrix is known as an idempotent matrix. Okay, now if I have an idempotent matrix, and also I have to find for the result of the expression, that is A plus identity matrix whole raised to the power 11. Now if I expand this expression by using the binomial theorem, that is 11c0 a to the power 11 plus 11c1 a to the power 10 into identity matrix plus 11c2 a to the power 9, okay, a to the power 9 into identity matrix whole square, and so on up to 11c11 a to the power 11c11 a to the power 0 and identity matrix to the power 11. Now if you compute the result, this result is going to be coming out as 11c0 a to the power 11. Now a to the power 11 plus 11c1 a to the power 10, sorry, is going to be a to the power 10. Okay, this is going to be a to the power 10, and similarly the result is going to be followed as 11c11, that is identity matrix, and let us write this identity matrix over here I. So we have this particular result. Okay, now the expression of this particular result will be simplified as, so if you look at this, that is A square is equal to A, that means A cube is equal to A square, and A square is also equal to A, that means all the higher powers of A is also equal to A. That means I can replace the higher powers of A from the first 10 terms, okay, from the first 10 times as A multiplied with 11c0 plus 11c1 and so on up to 11c10, okay, and the last term is going to be 11c11, that is going to be 1 into identity matrix, and this result if you compute, the result is going to be coming out as 11 into, now 11c0 plus 11c1 plus up to 11c10 is going to be 2 to the power 11 minus of 1, 2 to the power 11 into minus of 1 plus, okay, and this result is going to be 11c11, that is 1 into identity matrix. Now I have to find for the trace of these particular values. So the trace of this particular value is going to be coming out as, so the trace of identity matrix is going to be equal to 3, and similarly the trace of in multiplied with this particular value. So that means I have to look for the, now since the question it is said that find the sum of the diagonal elements of the matrix A plus identity matrix whole raised to the power 11. So write this question over here to the power 11, and the trace of this particular matrix is going to be coming out as the trace of A multiplied with 2 to the power 11 minus 1. So I can do this as, so if you look at the first element of the diagonal of values, there is 1, 4 and minus 3. So that is going to be 2 to the power 11, okay, 2 to the power 11 plus 4 times of 2 to the power 11 minus of 1 plus 1 minus 3 times of 2 to the power 11 minus of 1. Okay, now if you compute the result, why did I subtract the minus 1? Because I am adding the identity matrix value over here also. Okay, and similarly also for this also plus of 1. Okay, so if you compute the result, and you will find out the result is going to be coming out as, so all the 2 to the power 11 terms you club over here, and the result is going to be coming out as 2 into 2 to the power 11 minus 4 plus of 3 plus of 2. So this result is going to be 2 to the power 12 minus 4 plus of 3 plus of 2, that is going to be plus of 1, and 2 to the power 12 plus 1, we know that 2 to the power 12 is basically 4096 plus of 1, and that is going to be 4097, and the right answer to the particular problem is going to be option number D. So from here the right answer to the particular problem is going to be option number D, that is 4097. I hope you were able to solve this particular problem on your own. The only observation was over here, okay, that is A square is equal to A. That is, such a matrix is basically an idempotent matrix. I hope you have solved this particular problem on your own. Let us move to the next problem. Okay, so the next problem says that there is a matrix which is a 3 cross 3 real matrix such that transpose of the matrix P is equal to some constant times, that is A times of P plus A minus 1 times of identity matrix, and that constant A is basically I'm sorry, is basically greater than A, greater than 1. Okay, so we have to solve for whether the adjoint of P is equal to 1 or greater than 1 or equal to some value half, or whether P is a singular matrix. Okay, so let me assume the matrix P as a real matrix. So let us assume in this particular fashion, that is A1, A2, A3. Similarly, this is B1, B2, and B3. And similarly, this is C1, C2, and C3. Now, from here, if I do the transpose of this particular matrix P, this will be equal to, so all the transpose is only the diagonal elements remains the same. Rest all the elements get interchanged with the corresponding ij will get changed into ji. So this will become A1, A2, A3. This will become B1, B2, and B3. This will become C1, C2, and C3. Okay, so we got the transpose of this matrix P. Now let us move further and let us equate the P transpose is equal to A times of P plus A minus 1 times of identity matrix of order 3 cross 3. Now if I do so, I will equate this matrix. Okay, so that is A1, A2, A3, B1, B2, B3, and C1, C2, and C3. And let us equate it with the A times of P plus A minus 1 times of identity matrix. So this will be equal to A into A1 plus A minus 1. Okay, and similarly the rest element goes as AB1, and this will be going as, so let me check. um, okay, so that is a mistake. Okay, that is not AB1. Okay, this is going to be, actually this is A times of P matrix, so this is going to be A2, and this is going to be A3. Okay, and similarly this element will again become A B1. Okay, A B1. This is going to become A B2, A B2 plus A minus 1, and this is going to become A B3. Okay, and this is going to become AC1, AC2, and this is going to become AC3 plus A minus 1. Okay, and these are basically given to be equal. Now let us compare the corresponding element, because what is said by the equality of the matrices. And if we follow the equality of matrix, we'll get the condition, the first condition, that is A1 is equal to AA1 plus AA1 plus A minus 1. And from here, if I club the A1, so from here if I club A1, so A1 is going to be equal to 1 minus A is equal to A minus 1. So from here I will get the value of A1 is equal to, so from here I will get the value of A1 is equal to minus of 1. Okay, and similarly if you do the same steps for the other elements, okay, other diagonal elements, okay, you will get the value of A1 is equal to B2, and is equal to the value of C3 is equal to minus 1. So you will find these elements A1, B2, and C3. That means the diagonal elements or the diagonal entries will be equal to minus 1. Okay, these are the diagonal entries. And similarly if you solve for the non-diagonal entries, that is A2 is equal to AB1. Okay, A2 is equal to AB1. So from here if you solve this, similarly you will get B1 is equal to AA2, and from these two results if you solve for, you will get, so what I can do from here, if I put A2 over here, or I can put B1 over here, so I will get these values. A2 is equal to A square A2, and from there I'll get the value of A2 is equal to 0. Okay, so from here if I compare and if I take this on this particular side, and we know that the 1 minus A square, and since A is greater than 0 cannot be equal to 0, that means A2 should be 0 in order for this result to satisfy. So if A2 is equal to 0, so from there I will also get B1 is equal to 0. Okay, and if you do the same results for the non-diagonal elements, you will find that all the other elements, okay, the other elements will be 0, will be 0. So what you will find over here, that is A2 is equal to A3 is equal to B1 is equal to B3 is equal to C1 is equal to C2, all are equal to 0. So that makes a P as a very special matrix, and that special matrix basically is minus times of, so minus times of identity matrix is basically minus 1 times of identity matrix, that is minus of identity matrix of order 3 cross 3. Now for this minus of identity matrix, if you find the adjoint of P, okay, so adjoint of minus of identity matrix is going to be the same, the identity matrix, okay, and with a minus sign. And so if you take the determinant of that adjoint of that P matrix, you will get the value of adjoint as 1. Okay, so with this you will find that the option number A is the right answer to this particular problem. So if you have solved this particular problem on your own, this was fairly simple problem. You just need to assume the matrix on yourself and then do the needful calculation to get out to the conclusion that this type of matrix is basically a special matrix or a negative of an identity matrix. All right, so I hope you have been able to solve this particular problem. Okay, so let us move to the next problem. Okay, so the next problem says that we are given with a matrix. Okay, so we are given with a matrix A, and that matrix is basically 1 by root 10 times, okay, and 3 by root 10, and this is minus 3 by root 10, and similarly this is 1 by root 10. Okay, so we have this particular matrix, and there is another matrix B. The B matrix is basically 1 minus iota, so I basically is iota, and 1. So here it is also mentioned that I is basically root under minus 1. Okay, so we have to define a new matrix P as A transpose B into A. Okay, so there is a matrix B M, sorry, there is a matrix M which is defined as A transpose B into A. Okay, now we have to find for this particular inverse of the matrix, A into M to the power 2023, okay, A transpose. So we have to find the inverse of this particular matrix. So let us call this matrix as some matrix D matrix. Okay, okay, so let me understand what this particular question is of any set pattern or not. So to see that, let us compute an interesting result. We will find it over here, is that if you do A into A transpose, what you will find. So if I do A into A transpose, that is 1 by root 10, 3 by root 10 minus 3 by root 10 divided 1 by root 10, and if I do the multiplication with this transpose, okay, so if I do the multiplication with its transpose, so you will find this an interesting result, that is equal to, so from here, if you do this, if you do the multiplication with the transpose, I can directly see that the non-diagonal elements will be equal to 0 and the diagonal elements will be equal to 1. Okay, so with this you will get a special type of matrix, that is a identity matrix. That means computing A into A transpose, you got the result as identity matrix. That means A is basically an orthogonal matrix. And similarly, if you perform for B, so similarly if you perform B square, okay, so from here if you perform B square, okay, now since B is an upper triangular matrix, you will find another interesting result about the matrix B. That is, if you square the matrix B, and you will get the result something like this. So this is going to be 1 over here, this is 0 and this is 1, and this element will get changed, and this is going to be equal to minus of 2y. So if you perform B square, you get this particular result. And similarly, if you perform B cube, you will get the result something similar like 1 0 is 1 over here, and the upper triangular element, okay, this is going to be minus of 3i. So what you can observe is that when you are squaring the matrix, this particular element is going to be equal to minus of 2 times of I. Similarly, when you're cubing the matrix, you're getting the element over here as minus of 3 times of I. That means if you perform B to the power n, you will get the element over here as minus of n times of I, that is iota. So we have to perform for B to the power 2023. So if you have to perform for B to the power 2023, this is going to be, the matrix is going to look like this way. Okay, so from here, what is, okay, so from here you get the value of B. Okay, now if you have the value of B to the power 2023 as this particular fashion, okay, now it is said that M is defined as A transpose B into A. Okay, A transpose B into A. Now if I perform M square, this is going, result is going to be A transpose B into A transpose into A. So A into A transpose is basically going to be identity matrix. That means that is M square is again coming out to be, okay, M square is coming out to be, and this is going to be, and okay, so did I miss any, okay, yeah, I missed the B over here. Okay, so this is going to be A transpose B square into A. Okay, and similarly in the same fashion, if I perform 2023 M to the power 2023, I will get the result as A transpose B to the power 2023 into A. Okay, so the result will be something like that. And now if I perform A into M to the power 2023 into A transpose, the result is going to come out as A into A transpose B to the power 2023. Okay, A into A transpose, and A into A transpose is going to be identity matrix. So this is the result is going to be coming out as B to the power 2023. Now if you compute the value of B to the power 2023, the result is already found out as 10 minus 2023i, and this is 1 over here. Now I have to find for the inverse of this particular matrix. Okay, now the inverse of this particular matrix, okay, that is A M to the power 2023 A transpose. Now if I take the inverse of this particular matrix, so this inverse is basically going to be the inverse of this particular matrix. So the inverse of this particular matrix, if I write over here, I can write directly as 1 by determinant of this particular matrix. So if determinant is going to be 1, and similarly we just need to exchange the diagonal elements and the non-diagonal elements with a negative sign, and the non-diagonal element with a negative sign. Okay, so this is going to be the inverse of this particular matrix. So the inverse of this particular matrix is going to look like this. Okay, so that with this we will get the option number C as the option. Okay, as the right answer to this particular problem. So I hope you have solved this particular problem on your own, then you must have got to this particular conclusion. Now, a bonus tip to all of you, that whenever you see a question which involves a higher power of matrices, okay, there must be some important or interesting properties involved with that particular matrix to solve this particular question. Like in this particular problem, you see that matrix A is basically an orthogonal matrix, and similarly B is an upper triangular matrix, which simplified the product term. Okay, so I hope these particular results are actually helpful. Okay, so let us move to the next problem. Okay, so the next problem is fairly simple problem, and it is said that there is a matrix A which is defined in the fashion 1 over here, it is log x with the base y and log x with the base z. Okay, and there is a y with base x. Similarly, this is 2, and this is log y with base z. This is log z with base x. This is log z with base y, and this is 3 over here. Now I have to find for the determinant of adjoint of a square. Now this for finding out this, let us firstly find out what is the value of the determinant of a. So I will firstly do this in order to find the determinant of A. Now what I will see, what I observe over here is that, so the observation is very important. Okay, so what I can do, I can write 1 as, so if you know the properties of log x to the power base x is actually equal to 1. Okay, and similarly log x base y, it can also be written as log x base some common base a divided by log y with some common base a. Okay, with some common base a, and then this result can be easily established. And see, for doing this result, let us take common. So instead of 1, I'm writing this as log x base x. So for doing this, I have to divide by log x. Okay, so I am dividing my log x, log y base y, log x base x. Okay, and similarly log z base z. Okay, and I am dividing it, and then in taking the determinant value, what I'm doing, this is I'm writing it as log x. Okay, and this is also as log x. Okay, this particular value is also equal to log x. Okay, so what I observe is that only the base is different. So instead of doing that, what I'm doing, I'm dividing by log x by log x, log x by log y, and log x by log z, and I'm taking in the log z common, log x log y log z common, and let me represent it with some common base. Okay, so I'm writing this with a common base respect to 10. Okay, for example, that doesn't matter. Okay, because actually eventually you will find out that they are actually getting cancelled out. And similarly this particular result can be written as log y. Okay, this is log y. Okay, 2 times of log y, and this is again going to be log y, and similarly this result is going to be log z. This result is going to be log z, and this result is going to be 3 times of log z, and you take the determinant of that. Now what I see, from each and every first column you take log x common, on the second row you take log y common, and the third column you take log z common, and if you do so, this result will again get cancelled out, and eventually we end out finding the determinant of a as equal to, the determinant value of a will be similarly equal to 1 1 1 over here, 1 2 1 over here, and 1 1 and 3 over here. So the determinant of value will be simplified as this particular value. So if you solve out the determinant value of this particular matrix, okay, square matrix, this is going to be 6 minus 1 and minus 1 times of 3 minus 1 and plus 1 times of, so this is going to be 1 minus of 2, and from here if you simplify, this is 5 minus 2, and this is going to be minus of 1. So from here you will get the result of the determinant as 2. So 5 minus 3 is equal to 2. Okay, so you got to the value of determinant as basically 2. Now you have to solve for, okay, adjoint of a square, okay, adjoint of a square, and the determinant value of this particular. Okay, so you will find out this is basically equal to, so adjoint of any matrix. Okay, so I have already said this particular property, so let us not write it again. Okay, so I am directly applying the result. So adjoint of any matrix A square. So let us write this will be equal to A square determinant of, and the order is basically 3. So n minus 1 whole square. So that is 2 to the power 2. That is 4. And now, and this square, okay, and this can be also expressed as, okay, this is going to be determinant of A whole to the power 8, and that is basically equal to 2 to the power 8. With this, the right answer to the particular problem will be equal to option number B. That is option number B, that is 2 to the power 8. So the right answer to the particular problem is option number B. I hope you have solved this particular problem. Then you must have arrived to this particular result. So fairly simple problem which involves property and the value of calculating the determinant. Okay. So with this, let us move to the next problem. Okay. So the next problem is again an interesting problem. Okay. So if you look at this particular problem, so let us look at this particular problem. So it is saying that alpha is a root of this particular equation where a, b and c are distinct real numbers. Okay, so alpha is the root of this particular equation, then it must satisfy this particular equation, that is a minus c alpha square plus b minus c alpha plus c minus b is equal to 0. Okay, now a, b and c are all distinct numbers, and it is saying that this particular matrix is basically a singular matrix. So if it is a singular matrix, then the determinant value will be equal to 0. Okay, then determinant value will be equal to 0. So the determinant of this particular matrix is equal to 0, as it is said in the problem, as it is singular matrix. So from here, if I solve for the determinant value, I'll get the determinant as alpha square minus c minus b minus of alpha times of c minus a plus 1 times of b minus a. Okay, and this particular is equal to 0. Okay, now this particular matrix is singular only and only when, okay, now this particular matrix is singular only when the value of alpha, is equal to 1. Okay, you can observe over here. Okay, so if you put in place of alpha is equal to 1, if you put alpha is equal to 1, you will find that this result assembles this particular quantity. Okay, because it is said in the problem that if a minus c into alpha square plus b minus c into alpha plus c minus b is equal to 0, and in order to make this particular result also 0, in order to make this result also 0, okay, order to make this result also 0, this particular result hold true. So you can see if you put alpha is equal to 1, this result will hold true, and all of them, all c will get cancelled with plus c and minus c get cancelled, minus b plus b get cancelled, and minus a plus a will get cancelled out. So that means this particular result, okay, this particular result is singular if the value of alpha is equal to 1. So this particular result is singular only if the value of alpha is equal to 1. Now I have to calculate for the value of a minus c whole square divided by b minus a into c minus b plus b minus a whole square divided by a minus c into c minus b plus c minus b whole square divided by a minus c into b minus a. Okay, now I have to perform for this result. Now let us take the do simplify it. So if I take the denominator, okay, so the denominator is going to become b minus a into b minus c into c minus a, and the upper part, the numerator part, will be equal to, that is a minus b whole cube plus b minus c whole cube plus, and this is going to be c minus a whole cube. Now if all of them are distinctly 0, okay, now all of them are distinctly 0, so what I can find out over here is that, so if alpha value is equal to 1, so if alpha is equal to 1, so from here if I put alpha is equal to 1, so I will get the result as a minus c plus b minus c plus c minus b is equal to 0. Now when a dash plus b dash plus c dash is equal to 0, so if I write the result over here, a dash plus c dash plus b dash is equal to 0, then a dash cube plus b dash cube plus c dash cube is equal to 3 times of a dash, b dash and c dash. Okay, so using this particular algebraic property, so using this particular algebraic identity or property, we can write this particular result as 3 times of a minus b into b minus c into c minus a whole divided by b minus a into b minus c into c minus a, and that is going to be coming out the result. Okay, so if you compute the result, oh sorry, this is not b minus a, this is actually a minus b. So that is my bad. Okay, sorry. This is going to be a minus b. Okay, so over here a minus b, and so this result is going to be coming out as 3. So with this, the right answer to this particular problem is going to be option number A, that is 3. Okay, so I hope if you have solved this particular problem, you must have got the answer as option number A. Okay, so this was fairly again a simple problem, okay, which involves just some bit of calculations. Okay, so with this, let's move to the next problem, and the next problem is going to be the last problem of today's discussion. So it is said that there is a matrix A. So there is a matrix A which is of the fashion 0, 1, 0, 0, 0, 1, and this is 1, 0 and 0. Okay. Now this particular matrix is given in this format. Okay. And it is said that B0 is basically defined as a to the power 49 plus 2 times of a to the power 98. Now I have also given you the recurrence relation, that is Bn is basically defined as adjoint of Bn minus 1. Okay, so if you try to solve this particular problem and you have to look for only the determinant value of B4. So the determinant value of B4 will basically be equal to, so you can write this as this determinant of B4 is going to be equal to determinant of adjoint of B3. Okay, and similarly determinant of adjoint of B3 is going to be equal to, from here I am writing this result from here, that is going to be again equal to adjoint of B2. Okay, and similarly adjoint of B2 is going to be determinant adjoint of B2 is again going to be equal to, so B2 is again going to be adjoint of B1. Okay, so yeah, and the determinant value. Okay, and similarly again B1 is going to be the adjoint value of B0, and B1 is going to be the adjoint of B0. Okay, so I am taking again the adjoint of B0. Okay, so and the determinant value of this. So to find for this, so you can see the adjoints are repeated 4 number of times, and I've already told you the result for this particular expression is basically B naught, determinant of B naught, and the order of B naught is basically similar to that of A, and that is going to be 3. So it is basically n minus 1 whole to the power k. So this is going to be 2 to the power 4. So 2 to the power 4 is going to be 16. That is B naught, determinant of B naught to the power 16. So the result for the determinant of B4 is going to be B naught to the power 16. Okay. Now what I will do over here is that, so if I compute the result for a matrix A, so if I try to compute A square, so the A square result will be 0, 1, 0, 0, 0, 1, and 1, 0, 0, and multiplying it with the 0, 1, 0. So multiplying with, I'm sorry, what is happening? Okay, so 1, 0, 0, 0, 1, and 1, 0, 0. So take it over here. Oh, there is some kind of problem, an issue from my side. Okay, that is basically the pen is not working properly. Okay, so with this, if you compute this result, okay, so with this, if you compute this result, you will find this result is going to be some kind of interesting result. Okay, so actually, what my mindset is going to be, that is try to take out that a square or any power of a, that is a square or a cube or a to the power 4 as identity matrix. So what I perform over here, if I perform this result, the result is going to be 0, 0, 1. This is 1, 0, 0, and this is going to 0, 1, 0. Now if this result is there, this is basically a square. Now again I multiplied with a to get value of a cube, and so again multiplying it with a. Okay, so if I compute this result again, and I will get the value of a cube as, so if you solve this particular, you will get the value of a cube as identity matrix. Okay, so finally you will get the value of a cube as identity matrix. Okay, now if you have the value of a cube as identity matrix, that is b naught is basically a to the power 49 plus 2 times of a to the power 98. Okay, now in order to simplify this result, the result is going to be a times of 16 times into 3. Okay, or I can write this more better way as a cube to the power 16, a cube to the power 16 into a plus 2 times of a cube to the power 32. So if you perform this, a cube to the power 32 into a square, so if you see this is basically, and this a cube and a cube is going to be identity matrix, so this result is going to simplify as a into 2 times of a square. So a into 2 times of a square, and if you do this result, okay, and you can calculate this result, that is 0, 1, 0, 0, 0, 1, and 1, 0, 0, plus 2 times of, so 2 times of that particular value is 2, 0, 0, sorry, 0, 0, 2. Okay, the first row is going to be coming out as, so the first row is going to be coming out as 0, 0, 2, and that is 2, 0, 0, and that is going to 0 2 0. Okay, and this is the result, and if you sum up, the result is going to be coming out as 0 1 2 0 1 2, and this is going to be 2 0 1, and this is going to be 1 2 0. Okay, now if you from here, if you calculate the determinant of b naught, so from here if you calculate the determinant of this particular matrix, you will get the determinant of b naught, and you can do that on your own. So you can see this is the element is 0 over here, and so you don't need to calculate the cofactor of this particular element. So minus 1 into, so I'm writing over here minus 1 into, that is minus of 1, and plus 2 times of basically 2. So 2, yeah, so 2 times of, sorry, not 2, it is 4. Okay, 2 times of 4, so that is 8 plus 1, and that is going to be 9. Okay, 2 times of 4, and the determinant value of b naught is going to be coming out as 9. Okay, so from here if I had the value of the determinant as 9, okay, so I have the value of determinant of b naught as 9, and that means the value of this particular determinant of b4 is going to be coming out as 9 to the power 16. Okay, and 9 to the power 16 can also be written as 3 to the power 32. 3 to the power 32, which is the option number C, is the right answer to this particular problem. That is option number C. So with this, I have covered the entire important previous year question of matrix and determinant. I hope you will keep this all these things in the mind. Okay, so yeah, it was interesting to discuss the different questions. Okay, I hope you will be using this particular questions when you are revising the chapter of matrix and determinant. So that was all of it, and thank you.